Exercise 41.7. This exercise is to be solved manually. Consider the region enclosed by the graphs of y equal to 6x cubed minus 7x squared minus 8x plus 5 and the x-axis. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Part B. Provide a calculus calculation that yields the exact area of the region. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Alright, for a graphic approximation, taking a look at these two graphs here. One is the x-axis. Alright, that's pretty obvious what that's going to be. But what about this other one here? It is a cubic function. It's got a positive ax cubed term. And so that brings to mind one of two possible shapes. One being the cubic function graph that has only an inflection point, no relative extrema. And a second possibility being the cubic function graph that has an inflection point and a pair of relative extrema. Since we are somehow to have a region enclosed by these two graphs, I'm thinking certainly it is going to be the variety that has a pair of relative extrema. And it's going to be intersecting the x-axis as well. So I'm motivated to seek some x-intercept. So, like all x-intercept questions, let y equal to 0 and consider the result. Here we have that 6x cubed minus 7x squared minus 8x plus 5 equaling 0. What about this equation? Well, in the world of polynomial equations, I usually suggest 4 lines of strategy to be attempted in order, and first being extraction of roots. Nowhere in sight here. Second being obtain a factorization equal to 0. In this case, well, let's see, as factoring goes, there's no common factor, and it's not a trinomial. This has got 4 terms to it. We don't seem to have any factor patterns offhand. The sort of final frontier of factoring is to factor by grouping. Maybe a little bit of trial and erroring with this might be a success. Let's try it out a little bit here. I think I'll break down this, rewrite this minus 7x squared term as a minus 6x squared minus x squared, because that way I get at least something going with the 6x cubed. So in other words, we have this. And I'm just going to worry about factoring the left-hand side, sort of abandoning the equal to 0 equation idea for a few minutes here. And in the spirit of grouping, the idea I will do is these two together, this trinomial together. Now here, I got a 6x squared common factor for this grouping. Leave behind x minus 1. For here, alright, with this negative x squared as the leading term, make this a little more easy to deal with and factor a negative 1 out of it. So this would give us a minus, and then we have an x squared plus 8x minus 5. Try to subfactor here. We're looking at x and x. For this to have any chance of succeeding as a factor by grouping, I know I've got to have an x minus 1 here, which would then become a nice overall common factor. So minus 1, and that forces a plus 5 here. But you know what? Those are two numbers whose product is negative 5. Don't sum to plus 8. Not working. Okay, so that's a dead end there. However, I find I'm a little bit more persistent than just a single trial and failure in factor by grouping. So let's go back, try another grouping. And let's see here. Alright, maybe break up the minus 7x squared with a minus 3x squared and a minus 4x squared. That way the minus 3x squared will set up a common factor in the beginning here, and then this leftover trinomial, who knows, let's see. So here we start off with And now the groupings will be these two and then these three. Here is that 3x squared common factor, leaves behind, let's see, 2x minus 1. Alright, here, once again, a negative leading coefficient is a little confusing, so just take a negative 1 out at first, and that leaves behind 4x squared plus 8x minus 5. Alright, now trying to subfactor this. Let's see. Well, you know, we can, although there's a lot of trial and erroring, at first keep in mind we're trying to do factor by grouping. So you sort of look back over here and realize that the only thing that is going to be helpful is not just a factoring of this trinomial, is a factoring with a 2x minus 1 factor. So let's go ahead and say, okay, you know what? We know you got to have 2x minus 1 to be helpful here, and this has got to be 2x here, and now I need to have these last two multiplied to be negative 5. That puts a plus 5 there. Now we need to see if the inner terms and outer terms sum to 8x. We got the outers being 10x minus 2x sums to plus 8x. It indeed is a factorization there. Okay, so now the good news is the 2x minus 1 is now a common factor to the overall expression. Let's pull that off to the side here. It leaves behind 3x squared minusing the leftover, which is the 2x plus 5. And now we can rewrite this a little bit. And now we can try to subfactor this trinomial. Here's one of those trial and error ideas where you know you need to have 3x and x as the first terms. And now we can trial and error two numbers whose product is negative 5, getting the inner products and outer products to sum to negative 2x minus 5 here plus 1. Now that product is negative 5, inner products negative 5x, outer products plus 3x, net effect minus 2x. Okay, factorization there. Alright, let's bring back our equation here. So this was, by the way, all once upon a time an equal to 0 equation, and now we can solve easily by solving each factor equal to 0. Sort of do this in our head, I guess. X equal to, here that'd be 1/2, here that'd be 5/3, here's would be negative 1, and then I'll put them in ascending order as the final step here. X equal to, okay, let's see, negative 1, and then 1/2, and then 5/3. Okay, so got those x-intercepts. Alright, let's try solving this equation again, and this time suppose that you did not succeed with a factor by grouping, or you're not comfortable with that kind of factorization. It is something of an art. Okay, we could go to what is sort of the last resort of manual polynomial equation solving, and that is to seek a rational root. Alright, and so by the rational root theorem, the candidate rational roots for this equation would be any number we can make up by using a factor of the constant term in the numerator and a factor of the leading coefficient in the denominator. In other words, our rational root candidates would be, okay, plus or minus factors of 5. Alright, either you got 1 or 5 there. Factors of 6, it could be 1, 2, 3, or 6. Okay, well, let's just start with maybe the simplest guess of all, maybe 1. Try 1 out. Now, since I'm also very much interested in having the quotient upon divide by x minus the rational number, I'm going to use synthetic substitution, or a synthetic division, as we might describe it here, to do all the computations. So 1 in the box. Coefficients of this polynomial are 6, minus 7, minus 8, and 5. Leave a line, draw a bar, drop this down to get started, and multiply 1 by 6. Add these, negative 1. Multiply, add, multiply, add. Okay, well, we were not successful. However, there is information here. We also know that the value of this polynomial at x equal to 1 is negative 4. What else do we know by inspection? The value of this polynomial at 0 can be seen right away as being 5. Now look at that. So we have this positive value. We have a negative value at 1, x equal to 1. Well, by the Intermediate Value Theorem, there must be some number in between 0 and 1 for which the polynomial has a value of 0. And since it might very well be rational, we should try numbers in between 0 and 1. Let's see, what have we got here? A simple one like 1/2. Okay, success. So 1/2 makes the value of this polynomial 0, and therefore by the factor theorem, x minus 1/2 is a factor. How about dividing the polynomial by x minus 1/2? Here's the quotient in descending order. This is, after all, synthetic division, and so this leaves us with 6x squared minus 4x minus 10. And now our equation back here becomes this equal to 0. 6, 4, 10. Both sides divided by 2. Now to continue factoring, here's this trinomial. This is the traditional it's working. There's a factorization. And now we can solve this equation by solving each factor equal to 0. Could probably do that mentally. This would be x equal to 1/2. This would be x equal to 5/3. This would be x equal to negative 1. And finally, maybe we put these in ascending order. Okay, and this brings us to the same point we were earlier in the question. Time to proceed with our graphing. Now what I tend to do next to help think a little further about this is I'll just kind of sketch these on a number line. What is going on in my mind now is that cubic function graph. It looks like, just real roughly speaking, it's going to have to be something that kind of goes like up here, there, and there. Alright, so the numbers x. I think that would be nice to have a reasonably accurate graph. Will be, let's see, perhaps here, negative 1/2, the 0. Over here, let's say 1, looks good. And how about 4/3 as well? Okay, so those 4 points. Now, this means we need to compute the value of a polynomial at a number. There's two choices for that, right? One is direct substitution. The second is synthetic substitution. If it's going to be a bit complicated, I tend to go to synthetic substitution. If it's really trivial, I'll usually use direct substitution. Actually, in this case here, as far as direct substitution goes, there's another aspect that we could consider, and that's that we don't actually have to use the direct substitution in this form. We actually did arrive at a complete factorization. We have a factorization of the polynomial, and this can make the direct substitution a bit nicer. So this gives the direct substitution a little more favor in your decision. Alright, so let's get started here. We want to know the value at x equals to negative 1/2. So y of negative 1/2 equals, let's see, I think I will choose to use the factored form of this polynomial and go with a direct substitution. We get 13/2, also known exactly as 6.5. Y of 0 equals, alright, here's where it's easiest to go through the original expanded polynomial. Putting in a 0 for x, we get 5. Okay, how about y of 1, negative 4. Okay. Lastly, y of 4/3. I guess I'll go direct substitution since the factored version is sitting here available. At negative 35 over 9. Okay, that's very close to a negative 4, isn't it? Just for sizing it up here. Alright, well, let's see. Let's think about how we're going to proceed on the graphing then. These y's here went about as low as negative 4 to as high as, 6.5. Let's see, that would be a span of about 10 units there. Okay, 1 centimeter per unit, sounds good. And so for our y-axis, we'll go from negative 4 to 7 at 1 per tick mark. The x-axis, okay, let's see. Now when we graph this, the final x-axis, it's probably similar to this here. Let's see, we need to have thirds and halves available. What if we did it sixths? Let's see. If we do that, that makes everything kind of convenient. It spreads it out quite a bit. How much so? Let's see, that would be about 3 units, 18 centimeters, 16 centimeters. Okay, that's alright. We'll do that. X-axis. Negative 1 up to 5/3 at 1/6 per tick mark. Okay, we are ready to set up this coordinate system and graph away. Alright, so as far as a graph of the region goes, this appears about complete. Got the graph of the cubic function labeled and graphed. We have the important x-intercepts with their coordinates labeled, and we've got the enclosed region shaded and labeled as such, and we have the x-axis and y-axis both labeled and scaled. Alright, onwards to the graphic approximation of the area of this two-segment region. And let's see, I try to use some simple geometric shapes here. Looking at these, I also notice that the x-axis and y-axis have been scaled differently, so I want to contain myself to geometric shapes whose key dimensions are parallel to either an x-axis or y-axis. That way I can just use quick ruler measurements and not have to use like distance formula with 2 points and that sort of thing. Too complicated. Okay, so the shape I seem to see here would be I seem to like trapezoids a lot because they give me awfully accurate results, and the formula is easy to remember, and it's a very simple shape. So here I'll take a dashed line along this side. Now I have this base, of course being the x-axis, I need to keep this base parallel to the x-axis. Now I want to arrange it so that the excluded portion will exactly fill the void portion here. Of course, it's just a visual approximation. It's not really exact, but the better it is, the better the estimate. Okay, maybe about there. Okay, this section looks like a trapezoid would work here as well. Okay, and this second base must be parallel to the x-axis. Okay, so now I'm going to say that the approximate area is equal to that of these two dashed trapezoids. Okay, and you want to maybe make a little recall over here. Area of trapezoid, general formulation, average base times height, or formulated algebraically 1/2 b1 plus b2 times h. Okay, so here on our first one, 1/2. Okay, the first base, call it the bottom one here, that's 1 there and a half there, 3/2 plus. Okay, so this second base, ruler measurement, looks to be, well, 2.3 centimeters. Remember, these are 1/6 per centimeter. So this is, well, all right, somewhat more than 2/6. Let's we'll call it 1/3. Height or altitude. Okay, looks like 7 centimeters. That's 1 per centimeter. Okay, and now let's add to that 1/2. Here, this base goes from, well, 1/2 to 5/3. Alright, we are in sixths here. That means 3/6 up to 10/6. That's 7/6. The second base looks to be, okay, like 2.7 of these, and they were 1/6 apiece. Okay, so let's see, a sixth is like 0.16, so say 3/4 of that would be about 0.12. Alright, so we'll say 1/3 plus 0.12, that's 0.33, 0.45. The altitude of this, okay, very close to 4. Okay, and let's work this out a little further. And we're up to about 10. Okay. 10 square units. Okay, very good. Part B. Provide a calculus calculation that yields the exact area of the region. Using calculus to calculate the area of a region will mean first slicing up the region, then seeing if it's convenient to formulate the area of a slice, and if so, sum up those slice areas with a definite integral. So let's start by slicing with the most popular choice, and that is a thin vertical rectangle. Now that we have these slices, we would like to consider formulating the area of a slice. And since they're rectangles, well, it's just a matter of length by width. However, length by width, as simple as it is a little bit of a problem here. Watch the tops of these rectangles as we go across here. There's a change right here. The tops of the rectangles start off being defined by the cubic function graph, then things change. The tops of the rectangles are defined by the x-axis, and the bottoms of the rectangles undergo the same situation. They start off defined by the x-axis, then comes a change. They are defined by the cubic function. Okay, that's not too bad. We can work around that, but since we're going to have two different formulations for area of a thin vertical rectangle, we're going to have two integrals to sum them up. The first integral will sum the rectangles whose tops are defined by the cubic function graph. If we sketch one of those rectangles, we find that as far as length times width goes, the length is equal to y minus 0 equaling y, and the width is simply a dx. When we sum the rectangles whose tops are defined by the x-axis, we'll find that their length is defined by 0 minus y equaling negative y, and have a width also of dx. So now let's describe what we have in mind for a solution, and that is that the area of the enclosed region equals the sum of two integrals, each of which is a sum of thin vertical rectangles. And now, following our visualization, let's go ahead and record those two integrals. Alright, now a slight simplification is available. A negative y dx. We can change this to a positive integrand two ways. One is to factor a negative 1 out in front, but something else that we can do and have no subtractions running around, and that is to change this to positive and then reverse the limits of integration. And now it's time to do some antiderivative work. So an asterisk, a little bit of a subcalculation. Let's go down to, say, perhaps here, and let's get an indefinite integral of y dx. First substitute in the polynomial expression. Alright, this looks like it's going to be successive uses of the power rule for antiderivatives. So here we would have a 6x to the 4th over 4 simplifies to 3/2 x to the 4th. Here's minus 7x to the 3 over 3 minus 7/3 x cubed. Here would be minus x to the 2 divided by 2 simplifies to minus 4x squared. And here we would just have then a 5x. Since this is an indefinite integral, we're supposed to be recording all the antiderivatives here, so we need to put a plus c to accomplish that. But the one we want is the one with c equal to 0, so we can come right in here and claim this as being our cap f of x. And so up here what we've basically got is that we need to then compute cap f of 1/2 minus cap f at negative 1, then add to that, here would be cap f at 1/2 minusing cap f at 5/3. A slight simplification is available here. F of 1/2 and then f of 1/2, so that's two of those. So okay, this becomes 2f of 1/2 minus f of negative 1 minus f at 5/3. Alright, what about these evaluations? Now cap f is a polynomial function, and so the evaluation of it can be done one of two ways. We can choose between direct substitution or synthetic substitution. The synthetic substitution might be very efficient, and we notice that the numbers for x here, a couple of them are fractions. We notice this polynomial has got a couple fractional coefficients, so synthetic substitution is looking quite attractive to reduce the arithmetic by about 50%, at least in these two cases here. Maybe the f of negative 1 we can do with direct substitution. That should be pretty simple. Okay, so double asterisk to refer the reader down to our value computation section of this. First at bat, that f of 1/2, that's one we'll use synthetic substitution for there. So 1/2 in the box. Coefficients of f are 3/2, negative 7/3, negative 4 plus 5. Don't forget to put the 0 for the missing constant term. Draw the line. Drop this down. 3/2. Multiply. Okay, we need to go to 12ths here, so a 4/4 buildup and a 3/3 buildup there. Negative 28 12ths plus 9 of them. Net effect of negative 19. And multiply. Negative 19 24ths. Negative 4 needs a 24/24 buildup. That would be negative 96 minus 19. That's negative 115 over 24. Multiply. Negative 115 over 48. 5 needs a 48/48 buildup. So this would give us 240 minus 115 of these. Let's see, 240 minus 115, that's 125. Add. Okay, there's the value of cap f at 1/2. Okay, how about cap f at negative 1? Alright, negative 1 is so easy to work with arithmetically. I think we'll do direct substitution for this one. F of negative 1 equals, looking over here at cap f. There's that value there. The cap f at 5/3. Okay, that's another one that's arithmetically challenging. So let's go with the synthetic substitution to compute this. The 5/3 goes in the box. The coefficients again. Okay, so we got our three values that we needed to proceed further to the main equation. 2 f of 1/2. 2 of these, that would be 125 over 48. Minusing this, that's adding 31/6. Subtracting this, that's adding 325 over 162. Okay, it is this in reduced form. Alright, it's an odd number, so there's no factor 2 to cancel. Will a factor 3 be available? The old device of add the digits up, see if that's divisible by 3. 1 and 2 is 3, and 6 is 9. 16, 17. No, doesn't divide by 3. No factor of 3. We are in reduced form here. Just multiply out this denominator, and we'll be set. And finally, we could say square units. Okay, there is our calculus calculation. Wow. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Okay, to assess correctness, we want to side-by-side compare our two results thus far. First, look back at that graphic approximation we had. It was 10. And since we're just looking at the numbers here, the units of measure are both the same in each case. I just call it 10 for the purpose of this comparison, and taking our calculus calculation and recording it here. That calculus calculation was the 12671 over 1296. Alright, and we need decimal numbers to compare apples to apples here. This here, you could do long division. There's something that we could just sort of look at. Alright, so this is about equal to, alright, a little note here. Just do 10 times this denominator, and so you can say that, note that 10 is equal to 12960 over 1296, and that being the case, this number here, 12671, it's about 300 short of this, so that would be 300 over 1200. No, 300 over 1300. That's less than a quarter, so that makes it about 0.2. This is about 0.2 short of being 10, so this is about 9.8, more or less. And that's some great news for us, because that means these two results are, without exaggerating, are within 5% of each other, and thus consistent. Therefore, the solutions to A and B are likely correct. Alright, so there we are. And the only remaining thing that can sometimes slip by a calculation that is sort of as complex as this one is some sort of error that doesn't shake the final number too much, and that can kind of slip under the cracks here. That's why I like to make the final claim that the two solutions are likely correct. There still is a slight chance of error, but we are pretty thorough in assessing the correctness, and if something's gotten by us now, at least it was pretty hard to notice, not some flagrant error. That's what we're trying to avoid, making ourselves look like we do careless work, which we don't. Okay, very good.